Hi all. So we are continuing with our lecture of our subject EC303 Applied Electromagnetic Theory. We have been looking at module number 4, transmission lines. So in this lecture we are going to look at the input impedance of a lossless transmission line, and we are also going to look at something called as a reflection coefficient. So in the last class we have seen that if you have connected a generator with an internal impedance, let's say ZG, to a transmission line with characteristic impedance Z0 and is connected to a load with impedance ZL, the input impedance is given by Z0 into ZL plus Z0 tan H gamma L by Z0 plus ZL tan H gamma L, where you say that the generator is connected at Z equal to 0 and the load is at Z equal to L, and the distance between the load and the generator is L, and gamma is our propagation constant. And we also saw through an assignment that if you measure Z in at a distance of L dash from the load, which means it is at a distance of L minus L dash from the generator, where Z in is equal to Z0 into ZL plus Z0 tan H gamma L dash by Z0 plus ZL tan H gamma L dash. Okay. So this we have seen in the last class. Now let's look at some more specific case of a transmission line, which is the lossless transmission line. We have seen earlier that a lossless transmission line is a transmission line in which when the wave is propagating through the transmission line, it will not attenuate, it will not encounter a attenuation. That means the attenuation constant alpha is equal to 0. And we also know that the propagation constant is alpha plus j beta, implies for a lossless transmission line my gamma is equal to j beta. And we can see that the gamma is there in the expression, both in denominator and numerator. So we have tan H of gamma L is equal to tan H of j beta L, and tan H of j beta L is equal to j into tan of beta L. It's not tan H, it is tan. So this is the expression for hyperbolic tangent of a purely complex number or purely imaginary number. So I can substitute this in my expression here, and I can write the input impedance for a lossless transmission line as Z in is equal to Z0 into ZL plus j Z0 tan beta L by Z0 plus j ZL tan beta L. So this is the expression for the input impedance of a transmission line which is lossless. Okay. So, basically you are looking at the impedance at here Zin. Similarly, if you look at from here, that is at L dash, so you can write Zin at L dash is Z0 ZL plus J Z0 tan beta L dash by Z0 plus J ZL tan beta L dash. So, these are the expressions for the input impedance in a lossless transmission line. Now, let us look at some special cases. The first case is, what if you have a short circuited line? What do you mean by short circuited line? The load impedance is equal to 0, or in your circuit you have the characteristic impedance of the transmission line, and at the load you have just connected by another line, that is all. So, you can substitute this expression in Zn, that is Zn is equal to Z0, ZL is equal to 0. So, you have 0 plus J Z0 tan beta L by Z0 plus J into 0 tan beta L. This is equal to, you see the Z0 at the numerator and denominator gets cancelled, and there is Z0 here which give J Z0 tan beta L. So, for a short circuited line, the input impedance is equal to J Z0 tan beta L. Okay. Now, let us consider another scenario where the load is open, or you can say it is an open circuit, which means the load impedance ZL is equal to infinity. So, you have a generator, there is the transmission line with characteristic impedance Z0, and it is open connected, that is your ZL is equal to infinity. So, in this case, the input impedance Zin is equal to Z0 multiplied by, now I would like to make ZL at the denominator. So, what I will do, from this expression I will take ZL out from the numerator and ZL out from the denominator. So, I can write this as ZL multiplied by 1 plus J Z0 by ZL tan beta L divided by ZL into, this is ZL at the denominator also. So, this is Z0 by ZL plus J tan beta L. Okay. So, the ZL which is taken out common from both numerator and denominator will get cancelled. So, my expression for Zin will be Z0 multiplied by 1 plus J Z0 by ZL tan beta L by Z0 by ZL plus J tan beta L. Okay. So, ZL is infinity here. So, I need to take a limit which tends to infinity. So, Z in I can say is limit ZL tends to infinity Z0 into 1 plus j Z0 by ZL tan beta L divided by Z0 by ZL plus j tan beta L. Now, when you apply the limit, 1 by ZL, which will be equal to 1 by infinity, will become 0. So, this will become 0, this also will become 0. So, your final expression will be, this is equal to Z0 into 1 divided by j tan beta L. So, 1 by j is equal to minus j and 1 by tan beta L is equal to cot beta L. So, I can write Z in for an open circuited line as minus j Z0 cot beta L. So, I can represent this Z in as ZOC, which means Z input impedance at an open circuit line. I can also represent for short circuited line as ZSC, which is short circuited line. Let us take another condition in which you have the output load impedance is equal to the characteristic impedance of the line. Okay. So, this is called as a matched transmission line. We will see why it is called as matched. Fine. Now, let us substitute in the equation. So, Z in is equal to Z0 into ZL is Z0 plus j Z0 tan beta L by Z0 plus j into ZL, which is Z0 tan beta L. So, you see the numerator and denominator are same, so it will get cancelled. So, finally, you will end up with Z in equal to Z0. That means, the generator sees an impedance which is equal to the characteristic impedance when the load is connected with an impedance value equal to the characteristic impedance. Okay. So, you have the generator, you have this transmission line with characteristic impedance Z0 and you have the load impedance ZL is equal to Z0. If generator looks from here, it sees a input impedance equal to the characteristic impedance, which tells us many things. First thing, this is called as a matched because it will deliver maximum power to the load. So, the maximum power is transferred to the load when the load impedance is equal to the characteristic impedance of the transmission line. It also gives no reflections, or you say that there will not be any reflected waves. We have seen that in the transmission line there will be forward travelling wave and backward travelling wave. The backward travelling wave is called as a reflected wave. If it is a matched condition, then the complete power is transferred from generator to the load. There will not be any reflections from the load. We will also see numerically how it is possible. Okay, and this is called as matched condition, which is ZL is equal to Z0. So, these are some of the special cases of the lossless transmission line input impedance. We will regularly revisit these conditions again and again when we do Smith chart and other topics. But the basic thing is everything is from the input impedance side. Okay. Now let's look at a new parameter which is called as reflection coefficient. Okay. Now, reflection coefficient by definition is the ratio of magnitude of reflected wave to the incident wave in a transmission line. So, what do you mean by that? So, in any transmission line, if it is not matched, there will be forward travelling wave and reverse travelling wave. So, if you take a point A, that point A will have a wave travelling in the forward direction. That point A will also have a wave which is coming in the backward direction. Now, if you take the magnitude of the forward travelling wave and the reverse travelling wave, that is called as the reflection coefficient. So, by equation we know that the voltage at any point is equal to V0 plus e raised to minus gamma z plus V0 minus e raised to plus gamma z. And we also know that this is for forward travelling wave and this is for backward travelling wave or reflected wave. And by definition, it is the reflection coefficient we represent as tau for any point Z is equal to V0 minus, which is the reflected wave, V0 minus e raised to gamma z by V0 plus e raised to minus gamma z. This is equal to V0 minus by V0 plus e raised to 2 gamma z. Okay. So, this is the expression for the reflection coefficient at any point Z in a transmission line. Okay. Now, we also know that in transmission line generated at Z equal to 0 and the load is at Z equal to L. So, what is the value of reflection coefficient at Z equal to L? So, reflection coefficient has another meaning. It is also the amount of reflected wave at any point when compared to the incident wave. So, it means at any point how much of the incident wave has been reflected. So, if I say the reflection coefficient is 0, that means there is no reflection, all the wave incident has been transmitted. If I say the reflection coefficient is 1, which means whatever wave has been incident has been reflected. Okay. So, if you look at load, your value of Z is equal to L, which means tau at Z equal to L is equal to V0 minus by V0 plus e raised to 2 gamma L. Okay. But from the derivation of input impedance, we have seen that the value of V0 minus is equal to VL minus IL Z0 e raised to minus gamma L, and V0 plus is equal to VL minus IL Z0 e raised to plus gamma L. Okay. Now, this is actually V0 minus by V0 plus e raised to gamma L by e raised to minus gamma L, which is from this equation. Just substitute Z equal to L. Okay. So, let us substitute this equation in this. So, you can see that tau of Z equal to L is at load is equal to VL minus IL Z0 e raised to minus gamma L into e raised to gamma L divided by VL minus IL Z0 e raised to gamma L into e raised to minus gamma L. So, e raised to minus gamma L into e raised to plus gamma L is equal to 1. Similarly, this is also equal to 1 because it is 1 by e raised to gamma L into e raised to gamma L. So, I can write this as VL minus IL Z0 divided by VL minus IL Z0. I can again simplify this. I can take IL out. So, IL into VL by IL minus Z0 by IL VL by IL minus Z0. So, this is equal to ZL minus Z0 by ZL plus Z0, because VL by IL is the ratio of voltage and current at the load, which gives me the load impedance. Okay. So, our impedance or reflection coefficient at the load, which is tau of Z equal to L, or it is represented as tau suffix capital L, is the ratio of the difference of load and characteristic impedance to that of sum of load and characteristic impedance. So, this is the reflection coefficient at any point in the load. Okay. So, if you look at this expression, what if the load impedance is equal to the characteristic impedance? What happens? You see that the tau L is equal to 0 by 2 Z0, that is equal to 0, means the reflection is 0. When tau L is equal to 0, this implies there is no reflection at the load, or this means complete power from generator is transmitted to load. So, whenever there is a reflection, there is some power leakage. If there is no reflection, the complete power is transmitted. Okay. So, this is the reflection coefficient at the load. Now, in the transmission line diagram, generator, the transmission line, there is load. We have also saw that if you want to find a value of reflection coefficient at any point L dash, so this is at z equal to L, this is at z equal to 0, which is a distance L dash from the load, or at a distance L minus L dash from the generator. Let us say I want to find reflection coefficient at this point B, which is at distance L dash from the load. So, you see for this point the value of z is L minus L dash, because you are finding the value from z equal to 0 to z equal to or to that point, although it is a distance L dash from the point z equal to L. So, what is the reflection coefficient in this case? So, in this case, you see tau of z is equal to, let us write the general expression V 0 minus by V 0 plus e raised to 2 gamma z, which is that we have derived at this point. This is that expression. And tau of z at at z equal to L minus L dash is equal to V 0 minus by V 0 plus e raised to 2 gamma into L minus L dash. This is V 0 minus by V 0 plus. Let us expand the exponential part, this part. So, we will get e raised to 2 gamma L into e raised to minus 2 gamma L dash. We have seen that V 0 minus by V 0 plus e raised to 2 gamma L is actually the reflection coefficient at the load, which is tau L. So, I can write this part as tau L. So, my tau of z at L equal to L dash, at z equal to L minus L dash is equal to tau L e raised to minus 2 gamma L dash. So, let me write it again. Tau of z at z equal to L minus L dash is equal to tau L e raised to minus 2 gamma L dash. So, the reflection coefficient at any point on the transmission line, which is at a distance from distance L dash from the load, is tau L e raised to minus 2 gamma L dash. Now, we always look at distance from the load, because load is the one which always changes, or load is the one which always we cares about. For different load, how are the things that we want to design? So, we always have the reference point at the load. Even when you are using Smith chart, we always refer from the load. So, any distance L dash from the load, the reflection coefficient is tau L e raised to minus 2 gamma L dash. Okay. So, this reflection coefficient is generally called as voltage reflection coefficient. So, this is actually voltage reflection coefficient, because we are dealing everything in this with the voltage. We haven't mentioned anything about the current. Similar to voltage reflection coefficient, you also have current reflection coefficient, which is basically the ratio of the reflected current to the ratio of the transmitted current. At load, this ratio is, as we saw in the voltage, I0 minus e raised to gamma L by I0 plus e raised to minus gamma L. And this is equal to actually minus of tau L, where tau L is the voltage reflection coefficient at the load. So, your homework is prove that the current reflection coefficient at the load is the negative of voltage reflection coefficient. So, this is the homework that you want to see, and it is very easy because you can always substitute I0 minus as V0 minus by Z0, sorry, I0 minus as minus V0 minus by Z0, and I0 plus as plus V0 minus by V0 plus by Z0, and you will see directly there is a negative term coming, but you should do that proof so that you will understand how the reflection coefficient works. Okay. So, this is regarding the reflection coefficient, and reflection coefficient is a very important term, since it can easily be measured when we are conducting experiments in the transmission lines. Okay. So, we will stop the class here, and in next class we will see the standing wave ratio and the power that is being transferred. So, in this class, we just to recap, so we had looked at the input impedance that we had derived last class. We looked at the special case of lossless transmission line, where you have the attenuation constant is 0. So, we usually derive everything in terms of lossless transmission line because the numerical part is very simple. Once we have lossy transmission line, the derivations are a bit complex. So, we always start with lossless transmission line, which helps in understanding our concepts well. So, in lossless transmission line, alpha is 0. So, your tan h of j beta L will become j tan beta L, and you can substitute that in the said in expressions. And you have special cases where you have a short circuit. You saw that what is the input impedance of a short circuited line. You have an open circuit. You also saw that what is the input impedance of a open circuited line. And then there is an important condition which is called as a matched transmission line, where we see that if the load impedance is equal to the characteristic impedance, the input impedance seen by the voltage or input impedance seen is equal to the characteristic impedance, and in this case you will have the maximum power transfer and there won't be any reflections. This is called as a matched condition. Then we saw a very important parameter in transmission line, which is the voltage reflection coefficient, which is actually the ratio of magnitude of reflected wave to the incident wave in a transmission line. And from the equations we know the forward travelling wave and backward travelling wave. So, the reflected wave is basically the backward travelling wave. So, I think I will mention that. So, the backward travelling wave is actually the reflected wave, and the forward travelling wave is actually the incident wave. Okay, fine. So, we can take the ratio of ratio to find the reflection coefficient, and we saw the expression for the reflection coefficient. It also gives the amount of reflection at any point in the transmission line when compared to the incident wave. We also found the reflection coefficient for at Z equal to L, and this is actually tau L, which is the reflection coefficient at the load. And we found the expression for reflection coefficient at the load, which is equal to ZL minus Z0 by ZL plus Z0. We saw that when ZL equal to Z0, the tau L value is 0, which means there is no reflection at the load. The complete power from the generator is transmitted to the load. And we also saw at any point L dash, at distance L dash from the load, which is at Z equal to L minus L dash, we found that you can express the reflection coefficient as the product of the reflection coefficient at the load, which is tau L, with e raised to minus 2 gamma L dash. Similar to voltage reflection coefficient, there is a current reflection coefficient, and the value is minus at the load is the negative of the voltage reflection coefficient. You have an exercise where you need to prove this. This is a very easy proof. Just there is only one step in this, and also prove that. Okay. So thank you for listening. We'll discuss more about this in the class.